Today we're going to look at the last chapter material that's going to be on Exam 1. This is Chapter 3. And we're covering the periodic table and atomic structure. Those two go together. They fit perfectly. In fact, the periodic table is designed to tell you about the atomic structure of each of those elements. And I'll show you by the end of this chapter. You'll know how that works. All right. I got extra copies if you lost one in the between last Friday and today. Come on. There we go. Just a list of topics. We're going to skip over that because we're going to get to them anyway. The understanding how the atoms are constructed took many decades, and it required some very intelligent minds, but it also required some technology. Well, I'm going to steal my own thunder. I better not. Let's just say things really got rolling when John Dalton proposed his atomic theory. And did I cover that last week? I didn't do that yet, did I? Okay. Well, let me see. All right. Okay. I don't have slides on that, so I'm going to stick to this slide and talk about the historical development of the structure of the atom. John Dalton first proposed the atomic theory, and what it says is that, let's see, Dalton first. And Dalton said that elements are composed of small particles he called the atom. And this is the smallest part of an element that still retains the characteristics, the identity of the element. Okay? He also said that each element has unique atoms. That's where he differed with the ancient Greeks. The ancient Greeks, some of the ancient Greeks, had proposed an atomic theory where everything was made of these elementary particles. Where the Greeks missed the boat was they said everything is composed of the same atom. So they couldn't explain how you could get gold and carbon black out of the same atom. So they went into some stratospheric gyrations to try to make it work, but it never did. So this is where Dalton solved that problem. He says that each of the elements is composed of elementary atoms. There's a sign-in sheet back there too. But each of the atoms of different elements are different. They are unique. Right? Let me see. I know I'm going to leave something out. He also said that compounds are composed of combinations of these atoms. And that during a chemical reaction, atoms are rearranged. Okay, what he's trying to do with this theory is explain laws that had been proposed and proven up to that point. Let's see. That's what I get for teaching so many different courses. I can't remember what I talked about in what course. There was the law of conservation of mass. Proposed by Antoine Lavoisier, and he just says during chemical reaction, the mass of the reactants equals the mass of the products. You don't lose any mass in a chemical reaction. And the difference between a law and a theory is a law just says what happens. Under these circumstances, this always happens. Doesn't try to explain why. A theory tries to explain why. So Dalton said, this is why that law works. Because you're not creating atoms, you're not destroying atoms, you're just swapping partners. Okay? The law of definite proportions. That looks like an end, doesn't it? Simply says that when a compound is purified and identified and its composition is secured, such and such mass of one element, mass of another element, mass of third or fourth elements, that ratio is fixed no matter what the source. So for instance, we could go to a body of salt water and distill it, purify it down so we get a pure compound of H2O, water. Or we could burn hydrogen in pure oxygen and get water. That's right? Two different sources. Water has the same ratio by mass of hydrogen to oxygen. And this explains that characteristic. Simply composed of combinations, and the combinations in a compound are fixed. Right? We know now, after decades and decades, that the combination is not by mass, but by numbers. Then one of the laws that Dalton proposed, the law of multiple proportions, simply says that if you have a binary compound, you have two elements that are together in a compound, and you have different compounds made of those two different elements. If you normalize the mass of one of the elements, then the ratio of the second element in the series of compounds is whole number multiples. So here's how we understand it today. Say we have nitrogen and oxygen in a compound. This is one nitrogen, one oxygen. We can also have nitrogen and two oxygens or nitrogens and three oxygens. Those are three different compounds, but if the mass of nitrogen is fixed, or in this case the numbers are 1 to 1 to 1, then the ratios 1 to 2 to 3, whole number ratios. That's what law of multiple proportion says, and this also explains why that is the case. All right, so that's Dalton's law of atomic theory. Dalton's atomic theory. Let's see, I had a blown up copy of that one here. That will help me. All right, next, and I think I'm stealing my own thunder here by going into subatomic particles. I'm going to do it this way, historically speaking. I think stream of consciousness, it should work fairly well. So the next in line was J.J. Thomson. He was a British physicist, polymath. A full century later. And at this time, there was a fascination with electricity. They didn't know what it was. They just knew that it existed, and they knew that there were positive and negative forms of electricity. So they knew that the concept of the pole was well established, and negatives attract positives, and like charges repel one another. They all knew that. What J.J. Thomson did was to use one of those devices. It was a cathode ray tube. And stylistically, we would say it's like this. It's just a glass tube that's evacuated. And we have like a plate here and a plate here connected to a source. This is connected to a negative source, and this is connected to a positive source. And they're probably connected to each other. Let's see, I think negative should be, I can't remember if it's the big one or the small one. Anyway, it's like a battery. And you could change the content here. You could be pure vacuum. You could put in small amounts of other gases, so when you turn the thing on, whatever particles were moving would strike those atoms and make them glow, like neon lights, right? Those tubes that they twist into different shapes and letters and such, and they can be different colors. That's the same concept. Or you can put a device in here. You could put a block like that. Or you could put a little windmill like that. And if you did that, then the particles that were flowing, and they always flowed from this one to that one, particles would strike that windmill and cause it to spin. So that told the researcher that, and Thomson, that these particles have mass, because they transfer their momentum to that windmill. Or if you put just a partial, block like this, and then you have a phosphor screen over this side, so if something strikes the screen, you'll see a flash. What you see is that as these particles are traveling, they produce a dark spot here, and they produce flashes over here. Right? So those particles are traveling in a straight line because they produce a shadow. Well, one other thing is, if you have just a slight amount of that gas I was talking about, you could see the beam as it traveled. Then if you put an external electric field on this one, you could see that beam bend toward the positive. So that means the particles are negative. Or you could put a magnetic, introduce a magnetic field and also see them bend. And they knew, depending on the field, which way it would bend if it were positive, which way it would bend if it were negative. So Thomson established that particles coming from the source are always negative. And that means they have to come from the atom. So the atom, he established the fact that the atom has negative particles in it somehow. And so Thomson's model said that, all right, there are these negative particles in the atom. And we're working from Dalton's theory, right? These scientists stood on each other's shoulders over time. So he said, all right, this atom has negative particles in it. So the Dalton's theory just says the atom is a bag, right? It's a jelly-filled bag, and we don't know what's inside of it. We're starting to get at what's inside the atom now. these negative particles. Thomson also established the ratio of mass of the particle to its charge. So he had charge to mass ratio. He couldn't tell, he didn't have the equipment, he didn't have the, I don't know what the blocks were, but at this time, he didn't have a way to tell what the mass of the electron was at this time. But it was pretty certain that the mass of the electron was very small, because we could only account for a very small fraction of the mass of each atom with the electrons that were found. So, but the charge to mass ratio was a value that was fixed. He determined that, and then it's going to be used later. Let's see. This slide left out an important figure in there. And my mind's gone blank. Millikan. Robert Millikan. He was an American, and he took it one step further. He wanted to determine the size of an elementary charge. This charge value was in terms of coulombs. It wasn't in terms of elementary charge like one electron charge. It was in terms of coulombs, and that has another derivation that we don't need to go into. But Millikan wanted to find out how many coulombs could be attributed to a single electron. He wanted to find out the elementary charge. Okay, so he devised this experiment, which had a vacuum chamber, right? Had a vacuum chamber, and it had a viewing port on the side with a telescope. Right? So he could look in there, or his graduate students could look in there, and he had a make a bulb out of it, an oil mister, and he make very fine droplets of oil. And then the oil would pass through a plate like this, and the plate was charged. So he had this, I think this one was, this is the positive plate, this is the negative plate. Oh, and he also had to irradiate the molecules up here. And what that did was it knocked electrons off of, there must have been a target here of some kind. Knocked electrons off of that target, and then the electrons were attached to the oil droplets. And the oil droplets would fall under gravity. And if these plates were not charged, then he could watch them, and there was a scale on the other side that was calibrated to a certain distance, and he could tell, based upon a formula that comes from physics, how fast the drops were falling, what their acceleration would be. And then he applied the charge. And if he made the positive charge big enough, then he could actually stop the droplet, and it would sit there, because it would be attracted to this one and repelled by that one. It'd sit in the middle. And the calibrated value of that charge was read on a meter. And he listed the charge thousands of times. He repeated this experiment over and over and over. I bet he had graduate students doing it too. And what he determined was that every droplet had a different charge on it. So it had different numbers of electrons. But he said when he looked at the data, and he said they're all multiples of a single charge, of a smaller value. And he determined that smaller value is the charge on one electron. Okay? So he determined the charge on an electron, that's coulombs per electron. And then with this value over here, from Thomson's work, he was able to determine the mass of an electron. And I don't have that handy, but it was very, very small, as they expected. Okay? All right, so now we know that the atom is made of electrons. We know the size of the electron, the mass of the electron. That means that now we can quantify what's missing in the mass of an atom. If the mass of an electron is a certain size, then the mass of the atom we knew, and there had to be something else in there that was providing the mass. So what happened from there was they took this model and they said, all right, these particles are electrons, but the rest of the mass is in the jelly, and it has positive charges of equal value to the negatives, so that our atom would be neutral, because atoms are neutral unless you make them otherwise. Okay, so this model came out to be called the plum pudding model. Anybody ever eat plum pudding? It's pretty good. It's got little pieces of plum scattered throughout a pudding. Okay, the pieces of plum are the electrons, and the pudding itself is the positive charge. Okay, so this was the proposed model for the atom at that time. Okay, all right. Now along comes Ernst Rutherford, who was an English physicist. And Rutherford said that model doesn't make any sense, because if you've got negative particles, there's got to be positive particles. So he proposed a model for the atom where it's called the nuclear model. And he said he's proposing that the atom is composed of a very dense central nucleus, and it has in it all the positively charged protons. Okay, and the electrons are out here somewhere, right, in this space. That means, since they have very little mass, that if you fire some small particle through here, that most of the particles are going to go straight through and be detected on the other side in like a bright spot. Right? If they're straight lines, unless they strike that or come close to that nucleus, they're not going to be deflected. Okay, but if this model is correct and everything is so diffuse, then the particles that you fire at it are going to come through, and all of them are going to be in a bright spot. There'll be none detected at angles or anywhere else. So Rutherford proposed an experiment to see if his model or that model was correct, and it's called the gold foil experiment. So here's what he did. At this time, there was also a lot of work in radioactivity. In other words, unstable elements like uranium and radon and those elements that eventually killed Marie Curie and her husband both. They got cancer because they weren't protecting themselves. They didn't understand what radiation could do to you. But there were basically three forms. At that time, they knew three forms of radiation. There were alpha particles, which are essentially helium nuclei, right? 2+ charge. We have 2 protons and 2 neutrons. I'll show you how that works in just. I haven't shown you that yet, have I? Okay, it's coming. So you have the alpha particles. You have beta particles, which are essentially electrons that are moving really fast. Right? They don't have enough mass to use for this experiment. And then there are gamma rays, which is essentially high energy light beams. So this is the one that Rutherford chose. And what he needed was a source, and I don't remember what the source was, but he had a source in a lead container, like this. He had his source here, and out of this source were coming alpha particles. Okay, so he needed a target that he could make really thin, because he knew if there were too many atoms in the way, then the beam would just be totally blocked and you get nothing. So it was well known at that time that you could take gold and hammer it really thin. You know, like the gold foil that was placed on the state capitol, right? A couple of ounces cover that entire dome. All you have to do is hammer it really thin. So it's only a few atoms thick. Okay, so we had the gold foil as a target. Right? That's gold, right? Everybody nods in agreement. So he has the gold foil. And then what he needed was a straight beam. So he did what's called collimation. He put a slit right here. Let's see, let's move it up a little bit. There. So coming out of here, the alpha particles could go off in every direction, and they could also come through here and go out like that, or go out like this, or they could go straight. The ones that went straight could only make it through the second slit. Let's see, let's move that up a little bit. So now he had a straight beam, and strike the gold foil. Okay? Most of them, he should expect that they would just pass right through, right? Because they'd be on either side of the nucleus and go through the electrons, and nothing would deflect them. It's just too massive compared to the electrons. So his detectors, he had detectors out here. His detectors should show a very bright spot right there. But if his if his theory is correct, then if this positively charged particle got anywhere near the nucleus, which was positively charged itself, it would be deflected. So we should also see a spot over here, maybe here, here, like off axis. And then if the alpha particle actually struck the nucleus, it would be bounced back. So he needed detectors over here too. So when they struck here, they might bounce back like that or like that. Okay? So he conducted the experiment repetitively, just to be sure, and he found that this is what happened. His model was the superior model for the atom, the nuclear model. And that means that that model was dead. And that's, have I told you guys about theories, what happens when a theory goes bad? We didn't talk about that. Oh, that's probably because this is a one semester course. Well, I've told you the difference between a law and a theory, right? So I might as well tell you what happens when a theory goes bad. When a theory doesn't predict the way it should, and theories are good because they try to explain why, which means you can change the conditions outside the conditions that are required to make a law work. They're much more flexible. But when the theory doesn't predict as it should, you have several options. You can restrict its use. Okay? You can say these are the boundaries. Outside those boundaries, it doesn't work. So Newtonian physics works within a range of mass and speed. If you go too fast or you get close to a black hole, you can't use it anymore. You have to go to relativity. And that's the other possibility. I'll put that one 3 here. you start over. Throw it out and start over. Well, we got a combination of both. We restrict its use, and then we start over to fill in the blanks on the places that it doesn't work anymore. So large mass and high speed, close to the speed of light, that's relativity. Or very small, Newtonian physics doesn't work either, and that's quantum mechanics. The other thing you can do is modify it. Right? You can modify your theory to account for the variations. And that's where a lot of theories go. They modify it, and then they're modified, and they're modified to a ridiculous state. And if the modifications eventually fall apart, you might throw it out and start over. Okay? And then there's a fourth one that I add. You turn it into a religion. Right? You believe it without any supporting evidence. Right? And this is example. Man caused global climate change. That's now a religion. There's no support for it whatsoever. I mean, not as a single. Man didn't cause climate change. He may have contributed, but he didn't cause it. Right? There are other factors that are far more important than our activities. And the other one is Darwinism. Right? All species came from a single species, and they diverged over time to produce us. Those are two religions now. All right, that's what you do with the theory when it goes bad. The first three are valid, the last one's not, as far as science is concerned. Okay, so now we know that the atom is made up of a central thing with protons in it, and it could be more than one proton. It could be several protons, and then the same number of electrons would have to be out here somewhere, okay, to balance it. But what Rutherford also understood was, not even with all those protons, he couldn't account for all the mass of the atoms. Anything above hydrogen, you couldn't account for its mass with just protons. And some of the isotopes of hydrogen, you couldn't account for it either. So he had a graduate student who graduated and then worked with him further as a research assistant named Chadwick. And, oh, by the way, Rutherford got a Nobel Prize for this work. Then he put Chadwick on solving the problem of where's all that mass coming from. And Chadwick identified the neutron. Proved that the neutron was in that nuclear center. And he got a Nobel Prize for that work too. So he got two Nobels coming out of the same lab. Okay, now we know that the atom is composed of protons and neutrons in the nucleus, and then electrons out here. Okay? Now what we needed to do was identify what are those electrons doing out there. And here's why we need to know that. When two atoms, according to Dalton's theory, when you form a compound of these various atoms, when you form a compound, say these two atoms are approaching one another and they might want to form a bond, make a compound. What do they see first, now that we know the nuclear model? First thing you see is electrons. So what we want to know is, how do those electrons interact? And that means we've got to know something about their energies. Because when reactants come together and form products, the overriding rule is that they're not going to form products unless there's an energy advantage. stability is the key. Are the products more stable than the reactants for a spontaneous reaction? And for that to happen, products must be lower energy. It may be on a localized scale, and I'll give you an example in a second. But we need to know something about the energy of the atoms and the electrons around them so that we can say something about how they interact when they come together. Now, one possibility that that appears on the surface to blow that theory out of the water, where low energy on this side favors the reaction, is the production of nitroglycerin. Right? We know that nitroglycerin, when it's produced from sulfuric acid, nitric acid, and glycerol, produces an explosive compound. Right? There's a lot of energy stored there. Well, what happens is, if I draw this graph, right, and we're going to look at more graphs today, x-axis, y-axis. If I put on this one energy for everything, reactants and products, depending on where they are, and this is the progress of the reaction, then if we start off here, we would expect to end up over here, right? For a reaction to be stable, it'd have to be lower energy. But what happens with nitroglycerin is you add energy into that reaction, and then it reaches this peak and it hits a valley. And it's relatively stable there as long as you don't sneeze or look at it cross-eyed. If you do either one of those, it'll blow up in your face. And then, in order to get it to go down here and release all that energy, you just need a little kick. And then it'll go down there. And that's where you get all that energy back. But nitroglycerin sits right here. Okay? And Alfred Nobel spent years trying to figure out how to make nitroglycerin useful, because he knew it had a lot of energy available to do work. Eventually he combined it with kieselguhr, which is diatomaceous earth, and that stabilized the molecule. So in those dynamite sticks, right, that has nitroglycerin in them, as long as they're not sweating, you're okay. If you find a box of them, an old box of dynamite, and you are stupid enough to open the lid and look inside, and you see droplets on the casing or at the ends, close the lid very carefully and exit as quickly as possible, because it's sweating nitroglycerin. And nitroglycerin, without that kieselguhr to stabilize it, will blow up. And all it takes is just one of those little droplets to go, and it will set the rest of the case off. So, yeah, it's okay to handle as long as it's fresh. Now, we have other explosives now that are much more stable. Like the one you see in the movies, C4, right? Which just means composition 4. It doesn't say what's in it. The name doesn't say what's in it, but it's much more stable. In fact, it won't blow. You can't make it blow hitting it with a hammer. You need a blasting cap to set it off. You can even shoot it with a bullet and it won't go. Okay, so we would need to know something about the atom and the electrons, their energies. Along comes Niels Bohr. He was a Danish chemist, physicist. And he proposed the planetary model. So he took the nuclear model of Rutherford and he put some structure to it. He said there's this nucleus which has, just like Rutherford said, positive charges here, and there are energy levels out here. Distance from the nucleus assigns energy levels. And as you go further from the nucleus, the energy levels get closer together, like that. Okay? So this would be N equals 1. That was his, later on that's going to be identified as our principal quantum number. But at this time it was just a number that Bohr assigned to this level. This is as close as you could get to the nucleus with an electron. It's the lowest energy. Closer to the nucleus means lower energy. And in fact, Bohr's model only works for hydrogen or atoms that are like hydrogen, one electron only. They can have several protons, but only one electron. The reason his model doesn't go beyond that is because once you start adding more electrons out there, then they start repelling each other, they start getting in the way and complicating things. So we focus on hydrogen atoms or hydrogen-like atoms. So let's stick with hydrogen here. Okay, so if the electron is there, it's at what we call the ground state, the most stable position. The outermost electron is as close as it can get to the nucleus. If there are other electrons in the way, then it can't get any closer. That's also the ground state. But for our hydrogen atom, this is it, at n equals 1. If the electron is promoted to the next level, n equals 2, we have to add energy to get it there. So you could add energy by heat, by collisions, by light, okay? And you could promote that electron to the next energy level. So we would have to add energy. Say we do it with light, right? Then we could add energy and promote that electron to this one. We also know the energy of each photon of light that's striking it. So we can do a calculation. We can say the energy of the photon of this beam is a certain amount, and if it promotes to that level, then we know that's how much energy it took to go from one level to the next. And Bohr had a formula that we're not going to get into because this is an introductory course. But if that electron relaxes as it returns, it's going to give up that energy, the same amount of energy that it absorbed. It's going to give it up. Okay? All right. Now this explains what we see in, say, a hydrogen discharge lamp. If we have hydrogen in this little glass bulb and we shock it with electricity, then it's going to give off light. And in fact, it's going to give off light of specific frequencies. And in the visible range, there are only 4 of them. Okay? The reason it only gives those 4 individual lines is because each one represents an amount of energy. So the electron would have to relax from, if it relaxed from way out here down to N2, that would be the most energy. Be on the blue end of the spectrum. Right? And if it relaxed from closer, then that would be on the red end of the spectrum. And that's evidence, that line spectrum is evidence for the validity of Bohr's model. We don't get a continuous spectrum. We get a line spectrum because there are only certain jumps that are allowed. Nothing in between. Okay? Am I giving you too much? I'm trying to squeeze a whole semester into just a few minutes. Okay, so that was Niels Bohr. Now, so this was the model that was proposed by Bohr, and it stood for quite a while, for several years. And it started off with some, he had to ignore, with a planetary model, what happens with these electrons. We know from physics that a change in direction, a moving object, changing direction requires energy. Right? So if these electrons are changing direction as they rotate, as they revolve around the nucleus, they're losing energy as they go. So they should eventually spiral into the nucleus, but they don't do that. Right? So that's one of the problems with Bohr's model. The planetary model just doesn't fit reality. Okay, so along comes well, several scientists, but particularly Erwin Schrödinger. And Schrödinger took a different approach. He and several of his colleagues, a lot of people were working on this problem. But Schrödinger came up with the equations that described the wave nature of electrons. Up to this point, it had also been observed that light could be described as either a wave or as a particle, or as both, actually. That was Einstein's theory, his equations, that got him the Nobel Prize for the photoelectric effect. He was arguing that electrons have both wave and particle characteristics. So Schrödinger was approaching the electron that we knew was a particle already from previous work, but also the better description of the electron in its position around the atom was as a wave. So instead of a single particle, if you saw the electron as a wave, a standing wave could fit into this orbital. And only a certain standing wave, remember standing waves, they're in this circular pattern, the head has to come together to the tail at exactly the right point. So that would argue for different levels, and only those levels. Okay, so what grew out of Schrödinger's work and others was the quantum mechanical model of the atom. And quantum mechanics, when you're down that small, you're really dealing with, I want to say inexact, it's probability. What's the most probable arrangement? What's the most probable outcome from a test? Right? So it takes into account, the theory itself takes into account uncertainty. All right, so come on, there we go. So now I can run through these slides pretty quick because we've already covered this material. So now we know the atom is made up, it's a nuclear structure. The nucleus contains protons and neutrons. Protons carry the positive charge, neutrons no charge, but mass, similar mass to the proton, but very slightly larger, not much. And the electron possesses all the negative charges, and they're outside the nucleus. There's a ratio of masses, and you see if we set the mass of an electron at 1, then the proton is 1,837 times as massive. Right? It's still small, but it's a lot bigger than the electron. And then the neutron is just slightly larger than, than the proton. Okay. All right, so there's the nucleus, small, very dense protons and neutrons. The atom itself is neutral as long as the number of protons equals the number of electrons. And the number of protons identified on the periodic table as those red numbers is the number of protons. So the symbol and the element is joined at the hip with the number of protons, the atomic number. If you know the atomic number, it can only be one element. If you have the symbol or you know the element, it can only be one atomic number. You can't change the protons and have the same element. Okay, that's important to remember. When we form ions, when we charge an atom by changing the number of electrons. We don't touch the protons unless you want to change the element. Okay. All right. Let's see, I'm going to skip that one. Okay, so when we write the symbols, right, I'm going to use X because there's no X on that periodic table. So X could be any one of those. There are 4 places around this symbol reserved for specific information. We talked about the atomic number first, which we designate as Z, atomic number, the Z number. which is the number of protons. Okay? This position, the A number, is the mass number. And it equals the number of protons plus the number of neutrons. Okay? So if you have this value and you know that value, you just subtract this one from that one and you can calculate the number of neutrons. Okay? This position is reserved for charge. If there's nothing there, we assume it's neutral. Or you can write a 0 there if you want to. So it could be +1, +2, +3, or -1, -2, -3, or nothing. Down here is the number of atoms. So if you have a compound and you have a certain number of atoms in that formula, that's where you put the value, the subscript. Right? And when you're writing compounds, I can't emphasize this enough. When you're writing compounds like water, you don't do that. But it has to be a subscript. Like that. That would be the correct way to write water, H2O. Okay. Okay, and here's your symbol. I already showed you that. Now the significance of the number of neutrons in this value, this can change. Okay? That is fixed for whatever element it is. But this can be different for different atoms of the same element. And if they are different, then you're looking at 2 or more isotopes. That's where we get isotopes. So in this example, we're showing 11 protons and 12 neutrons to give you a mass number of 23. And these values are always whole numbers because we're trying to describe the character of that particular atom. And we can't have fractions of particles. All right. So an element is a pure substance. That is, it cannot be broken down further into simpler substance by either chemical or physical means. You cannot break it down into its elementary particles using chemical means. Okay? Now you can break it apart by nuclear means. Like we put it in a nuclear reactor, put an element in there and fire neutrons at it, and they could either capture the neutrons or they could add it and they could be blown apart. You know, various things could happen. But now you don't have the same element. But if chemical means are all you have available, you can't reduce it any further. It's simple and pure, and it only has one identity. In other words, if you break it apart, if you break this apart, you're going to get 2 different elements. You're going to get hydrogen and oxygen. All right, so we broke that apart into its simpler parts, and those simpler parts are elements. So this is made up of 2 different elements. Okay, that's just, I'm hammering this point home. Right. The number of protons, the atomic number, must be the same for all the elements of that particular type. So nitrogen has 7 protons, argon has 18, manganese has 25. Now the story of how we came up with these atomic numbers is, well, I don't think we have time to go into it. I'm going to eat up too much of your lab time. But there was, let's see, I had his name on the tip of my tongue. I can't remember it now. Who did the work that identified atomic numbers for the individual elements. I'll think of it in a minute. What I ought to do is add it to my slide set. Then I won't have to remember it. Yeah.
The first chart, how many analysts was on it?
Oh.
When I graduated school, there was only 105. There's up to 118 now.
Yeah, there's a total of 118 so far. The first periodic table was produced by Mendeleev, and it wasn't even that way. It was like twisted right angles. The second time he published it, he moved it that direction. And we're going to talk about the structure of the table in a minute. I think we get into Mendeleev and his contributions.
I think a lot of them was found like in the 1900s.
Well, yeah. As analytical techniques became more refined, they could identify smaller and smaller amounts in nature. And some of those elements that were once only man-made were eventually found in nature. But all of those that are in the, like the ghost-looking ones, like on the bottom list, NP for neptunium, plutonium, americium, all those are man-made. Technetium, right in the middle of the table, TC, that's man-made. We don't find that in nature. And all those that are on the post-its, those are all man-made also. Okay, so the problem with that for us as chemists is we really don't have a complete picture of their physical and chemical properties because they don't make enough of them to experiment with. So we have to infer their properties. But I didn't have you memorize any of those. Right? Remember the handout I gave you with the red boxes? There's about 60 of them. Those are the only ones I want you to memorize because they're the only ones you're going to encounter.
I know NASA used plutonium on their satellites to keep it this quick warm. There's only like a pound of it on Earth, so I mean, they're running out of it and they're trying to use it wisely.
Yeah, right. It's a product of nuclear reaction. Yeah. And they need a particular type of reactor called a breeder reactor to produce it. Breeder reactors usually work from uranium, and they have certain composition of their uranium. U-235 is the fissionable one. U-238 is non-fissionable. But during the reaction, the 238 picks up neutrons and produces plutonium by its decay. Okay, I mentioned isotopes. An isotope is the same element, but different numbers of neutrons. So we didn't touch the protons. We didn't even touch the charge. We just changed the mass. So if you're going to separate them, you have to do it based upon differences in mass because their chemical behavior is identical to one another. You can't do it by chemical means. You have to do it in a mass spectrometer. And I don't think I have a picture of one of those, do I? No. There might be one in your book. A mass spectrometer simply charges the atoms. So you have a mixture of isotopes. It charges the atoms and it accelerates them through an electric field into a magnetic sector. And the magnetic sector causes them, since they're charged, movement in a magnetic field of a charged particle will cause it to bend. The ones that bend the most are the lightest ones. So say we had U-235 and U-238 in there. 235 would bend the most, right? We could detect it over here, and then 238 would bend less because it's more massive. The same force is applied to each one. The more massive one takes more force, since it's the same force, it doesn't bend as much. And you can You can identify composition based upon the detector's response to how many strikes it gets. Some of them are actually built to isolate, to collect those isotopes. That was one of the ways that was proposed for acquiring U-235 enough for a bomb. These cyclotrons, which is a modification of the spectrometer. Okay, I don't want to go off on another tangent, sorry. So we don't have infinite time. Okay, so here's an example of two silicon isotopes. Notice the difference in the mass numbers. Right? So the first one has 14 neutrons, the second one has 15 neutrons. That's the only difference between those two atoms. Okay, suppose we have an isotope, X. Right? We have this isotope X, and we're told that it has 23 protons. Okay, so we can write 23 there, and it has 28 neutrons. Right? So its mass number is going to be 51. Right? Add those two together. Right? So that's the mass number. How about the element? Can you find the element? Yeah, 23 protons. Just look at the periodic table. Go left to right, top to bottom, things get bigger. So we work our way down and we find that 23 protons is vanadium. Okay? I don't think I had you memorize that one, did I? Oh yeah, maybe I did. Yeah, I think vanadium is in there. But that's fairly easy. Okay. Now, here's where some students get confused. When we write that symbol with the mass number is a whole number because it's the addition of protons plus neutrons, and those are whole particles. But when we put a value in the periodic table, in this periodic table, it's in the upper left-hand corner of each one of those boxes. That is a weighted average of mass values for each of the isotopes. The relative abundance of isotopes is different for each element in nature. Right? So here, this example, we have carbon-12, right, with 6 neutrons, has 98.89% abundance. So most of the mass of naturally occurring carbon is going to be due to that isotope. Okay? We just want to figure out what's the contribution of that one to the overall. And then the second one is carbon-13, which has 7 neutrons. It's only 1.11% abundant. So it contributes a little bit of extra mass. Right? So if, look at it this way. If most of the mass is due to carbon-12, but it's only 98.89%, then what contribution does carbon-13 have, and what should we expect for the outcome to be? It should be slightly larger than 12 because we're adding some 13 to it. Okay? And then carbon-14 is radioactive and insignificant, so we don't bother with it. We don't bother with it. There are people who spend their entire lives working on this stuff. Right? They just, they work out to the 6th, 7th, 8th, 9th decimal point. Right? We don't have to worry about that. As long as we stay within the first 2 decimal points, then we're good on periodic table from the 1900s on. Okay, this is, instead of the mass number now, we call this the atomic mass. And it's always going to be a fractional value. Even for carbon, it's going to be a fractional value. All right, here's the thing. If we're going to describe the mass of individual elements and their isotopes, we have to have a standard because everything's so small. I mean, we can't pick out an individual atom and put it on a balance. It just doesn't work that way. So what we have to do is say, all right, we need a standard, and we compare everything else to that standard. So we just arbitrarily, well, not so arbitrarily, but it appears that way. We say that this one, that isotope of carbon, has a mass, that atom has a mass of infinite zeros atomic mass units. That isotope, we fix it at 12 atomic mass units. Now, one atomic mass unit is roughly the size of a proton or a neutron. Okay. So once we fixed that one, then we can compare these, everything else to that mass. Let me go to the next slide. Okay. So 98.89% of naturally occurring carbon we can attribute to 12 atomic mass units. Okay. So since percent is a dimensionless number, and 98.89 times 12 is going to give us something just unusable, I use the decimal version of percent, which would be what? Move the decimal to the left 2 places. Right? Since you get percent by dividing this one by that one times 100, right? Just take the 100 away. Instead of dividing times 100, we're going to divide by 100 and get rid of the percent part and turn it into a fraction. So if we say 0.9889 times 12, and we do the same thing for carbon-13, right? Move to the left 2, that'd be 0.0111 times 13.0034, right? 13.0034 is its relative mass to the carbon-12 isotope, right? Nothing else but the carbon-12 has infinite zeros. Everything else has a fractional value. So when the contribution of 12 is 0.9889 and the contribution of 13 is 0.0111, then you add those together and you get 12.01. That's why on the periodic table, if you round to 2 decimal places, the atomic mass of carbon, naturally occurring carbon, is 12.01 atomic mass units per atom on average. Okay. Now here's the question that checks to see if you understand what I've said. If we isolate one atom from our sample of pure carbon, right, what's the probability that that atom will have a mass of 12.01 atomic mass units? Zero. It's a weighted average. No atom has that mass. It's a weighted average of lots of atoms. Okay? It's a weighted average so that we can actually use that information in the lab, because we don't have the equipment to isolate one atom and conduct a reaction with it. It just doesn't make any sense. Okay, so 12.01 atomic mass units is not the mass of any individual atom. It's a weighted average. It's kind of like your GPA, right? When you calculate your GPA, right, the carbon-12 would be like an A, and carbon-13 would be like a B. But if you get, no, carbon-12 would be like 4 credits, and carbon-13 would be like 1 credit. So if the top one is represented A, then 4 times A is 16 units, and the bottom one's only 3 units. So the contribution is greater for the more credits you have per course. So this course with 4 credits, an A in this course is worth a whole lot more than a 2 credit hour course, if you got an A in that one. And so when you calculate your GPA, the A in this course boosts your average more than a 2 credit course. Okay? That's what we're doing here, in effect, is a weighted average. Okay, let's see, it's after 10. Okay, I got till 11:30, right? Yeah. To finish this lecture. How far along? I'm not very far along, that's the problem. All right, let's take this example, for instance. An element consists of 62.6% of an isotope that's 186.956 atomic mass units, 37.4% of an isotope with a mass of 184.953 atomic mass units. What's the average atomic mass? So we would have one isotope is 186.956 atomic mass units. What's its abundance in decimal fraction? 0.6260. 0.6260. That's the fraction of this isotope that contributes to the overall. And then the second one is 184.953. 593? 953. 953. And then its abundance is 0.3740. 0.3740. If I hadn't said it before, if you write a number with a decimal hanging out here by itself, it's wrong. I don't want any orphan decimals in my field of vision. If you got a decimal to the left and there's no other number out there, put a 0. Okay, so if we do this calculation, the contribution of this isotope is a value and the contribution of this one, then we add them together to get the weighted average. All right, so 0.626 times 186.956. Oops, try that again. There we go. This is 117 point, let's see, 4 significant figures. So I can say 0. And this one is 0.37 times 184.953. And that's 68.4. Yeah. And we add those together. And that is 185.5 atomic mass units. And this is the average of those two isotopes. So we should have the average there. Well, how did he get? I made a mistake, didn't I? Let's try that again. 0.626, 186.956. Yep. 117. Maybe I ought to take this out and then reduce it. And then the second one, 184.953 and 0.374. Yep. So that's, oh, I did make a mistake. That's 69.17. So if we add those together, I get 186.2. Okay, that's the average atomic mass for that element. Now, how do we find out what the element is? Which one is it? Well, we don't know the mass, we don't know the atomic number, right? But as it turns out, as the atomic numbers get bigger, the mass numbers get bigger too. So if you just follow the table down, looking at the mass numbers, 186.207, I have to get a little closer. It looks like rhenium is our best bet, based upon its atomic mass. Just look at the periodic table and there it is. Okay? atoms of an element that contain, this is isotopes. Now we're going to look at the periodic table and how it's structured. We're going to look at its basic structure first, and then we're going to go into the atom itself and see how it aligns with the periodic table. Okay. And what I'm talking about there is electronic structure. Okay, periodic table is based upon the periodic law. What Mendeleev and a couple of others recognized was the periodic nature of the elements that they could be grouped together based upon their physical and chemical characteristics. So Dobereiner came up with the triads. He said these three elements have similar behaviors, like fluorine, chlorine, bromine, or I think it was chlorine, bromine, and iodine were a triad, halogens. They had similar chemical behaviors. He came up with some others like chalcogens, oxygen, sulfur, and selenium. They had similar characteristics, but that's as far as he took it. And then Mendeleev came along and arranged things in these groups, and he noticed that there were, if he went by mass, atomic mass, which is all they knew at the time, they didn't know about electrons and protons and such. He said, wait a minute, I've come along here with this group, and there's a gap in here that shouldn't be there. In other words, if I put, say if we're looking at nitrogen, phosphorus, arsenic, well, now that's not a good one. Carbon, silicon, germanium. He was going along, he says gallium fits with boron and aluminum. Right? Then you go over to carbon, silicon, and the next one that we know of is arsenic. He says if I put arsenic in there under silicon, it doesn't fit. It doesn't have similar characteristics to carbon and silicon. So he says, I'm going to leave that one blank. And I'm going to put arsenic over here with nitrogen and phosphorus because of its characteristics. But he didn't just stop there. He knew enough to predict what the element in that position would be like. It hadn't been discovered yet. So he said, okay, it's going to have approximately this atomic mass number. It's going to be atomic mass. And it's going to have these characteristics, these chemical characteristics, which are similar to carbon and silicon. And he said, okay, I'm going to leave that one blank, and I'm going to say, this is what you should expect to find, and put in that place. And lo and behold, years later they found it. So that's why, and he did that for several of the elements. That's why Mendeleev gets credit, the lion's share of the credit for developing the periodic table, because he used it to predict the behavior of atoms and elements that hadn't been discovered yet. Now the periodic law itself, notice how the table is arranged. The rows are called periods. And as you progress from left to right, you get one more proton each time you step to the right, and a heavier element, and it changes its chemical behavior. And then you go all the way to the end, and say you get from potassium, you go all the way down to krypton. And the next one, the next heaviest one from krypton is rubidium. But if we put rubidium out there, we're starting a new column. But rubidium behaves like lithium, sodium, and potassium. So why not put it over there with those? Just circle back, as our former press secretary used to say a lot. So that's known as a period, where you go down to the end and you start over again. And it comes from the concept of periodic motion. Has anybody had physics or physical science in here? You know what periodic motion is? Something is definitely moving, but it's not translational. It doesn't go from here to there and stop. It goes from here to there and then comes back to where it started. That's the period. One period out here and back, like a pendulum. Goes out, comes back. So we go out and we come back, start over. Go out, come back, start over. That's why it's called a period. Okay, and the table is an arrangement of those periods so that elements in the columns are grouped together according to their similar chemical behaviors. So the columns are called groups. We used to call them families. I don't know why we stopped doing that. Now they call them groups. And then the rows are periods. All right. So there's Dobereiner and the triads. Meyer, Julius Lothar Meyer, was working about the same time as Mendeleev was, and he proposed the concept of valency. And valency was an attempt to describe what was happening when elements of the same group reacted with elements of another group. We'll come back to that one. He produced a table, but he made no predictions whatsoever. So that's why Mendeleev gets the credit. So I described germanium as one of them. Technetium, the TC, is man-made, right? So that one didn't come along till way, way, way later. But he did leave a spot for it. It's radioactive. Doesn't occur in nature. And gallium also was missing. So he had gallium and germanium back to back. He had to jump from zinc to arsenic and leave those two places blank, describing what to expect in the future. There he is. Couldn't remember that guy's name. Henry Moseley. Henry Moseley was absolutely brilliant. He was working with X-ray spectroscopy. He would fire X-rays at pure elements and measure the light that came off of them, the emissions that come from them. And he could measure the wavelengths of each of the lights, the photons that come off of them. What he didn't know at the time was, when he was firing X-rays at them, he wasn't exciting the electrons. He was going down, he was exciting the protons in the nucleus. And they were emitting high energy wavelengths of light. What he did find was that he created this formula, and he could predict the emissions from each of the elements if he just changed the number, one whole number to the next. So if he was looking at emissions for iron, he'd put a 26 in there. If he was looking at emissions for bromine, he was using metal, so I better stick with that. Zinc, he would put a 30 in that formula, and it would spit out the exact wavelength for the emission light that he was getting. And it matched every time. So that was his atomic number. He didn't realize at the time that what he was doing was he was describing the number of protons in that nucleus. That was the height of his research. Because I think he was 24 at this time. Maybe later, 24, 25. He published his work in 1913. He was a patriot for England, and when they went to war with Germany in 1914, he enlisted in the army and went off to, I forget where, Gallipoli, I think. No, not Gallipoli. It was Turkey. I think he went to Turkey and died in battle. So that was the end of his research. Henry Moseley. Okay, So the periodic table, and this is good information for you when you're doing that extra credit periodic table, if you haven't already started it. The first column, well, I'll tell you what, we've identified horizontal rows as periods and vertical columns as groups. Now we can also subdivide or name some of those groups. The first column on the left, lithium, sodium, potassium, rubidium, cesium, and francium, that is known as alkali metals. Now the numbering system now is from left to right 1 through 18 on the columns. We used to, like when I was a student, we would have 1A is the first column, second column is 2A, then you skip over to boron, that's 3A, 4A, 5A, 6A, 7A, and then 8A. We used to have an 8A, that one says 0. That's useful information, and I'll describe what it's good for later. But when you're filling out your extra credit, we use the 1 through 18. Okay? The alkaline earths are the next column: beryllium, magnesium, calcium, strontium, barium, and radium. Those are alkaline earths, or alkaline earth metals. Then if we go to the far right, we get the noble gases: helium, neon, argon, krypton, xenon, radon. Radon is radioactive. And in fact, that's the one that they say seeps up into your basement, right? And if you don't have a way to evacuate your basement, then it just collects, because it comes up from the earth, from a radioactive decay in the earth, and it gradually seeps up and comes into your basement. I don't think it's quite as bad in my basement, because the first thing I did, and not for that reason, but for the dust, was I acid washed the floor, which is concrete, and then I went in with a sealant paint, and I painted the floor and the walls, everything. So nothing's getting through that. Okay, so noble gases, and then if you move just to the left of the noble gases, the fluorine, chlorine, bromine, iodine, astatine, those are halogens. And we used to have lights in our cars that had the little bulbs in them in the center that you could replace. Those were full of, I think it was iodine. They were halogen bulbs because they were a lot brighter, but they had kind of a off color, like a yellowish green. And some of the parking lot lights that you'll see around have that hue, and they're still using the halogen bulbs in those guys. More and more they're switching to LEDs because they're more efficient. And then next to them is the oxygen group. They're called chalcogens, CHALCOGEN. That's a holdover from older days when metals that are combined with oxygen are called calx. So the oxygen group is chalcogens: oxygen, sulfur, selenium, tellurium, and polonium. Polonium's radioactive too. And then the next one over is the nitrogen group, or pnictogens. Starts with P, the P is silent. The pnictogens, nitrogen, phosphorus, arsenic, antimony, and bismuth. And if you've ever taken Pepto-Bismol for an upset stomach, or you've swallowed bismuth. It's in a compound called bismuth subsalicylate. It's got this salicylic compound in it, which is an anti-inflammatory. It's like aspirin. Salicylic acid is, acetyl salicylic acid is aspirin. So that salicylate is what reduces the pain. Okay, the others, the central group, starting with scandium over to zinc, and then everything below that, except for the two bottom rows. We'll talk about those in a minute. Those are transition elements, or transition metals. Okay, here's a, let's see, that in this one it's in green. Those greens are transition metals, or transition elements. Now, one that may not show up here, and I'm thinking of it now, so I'm going to tell you. The first 2 columns and the last 6 columns, right? Lithium, beryllium, boron, over to neon. All of those elements are called representative elements. So if you see a reference to representative elements, those are the ones they're talking about. Now the last 2, the one that starts with lanthanum, cerium, and then actinium and thorium, the lanthanum row is called lanthanides, and the actinides are the second row below. And you'll notice that the, well, I'll do it over here. I mean, you can see it over there, but over here, maybe I'll be on camera. They fit right in here. The lanthanides fit in that gap, and the actinides fit in that gap. You'll notice we go from 89 protons to 104 protons. Well, the jump occurs down here, 90 through 103. Goes right in there. There are 2 reasons for that. One is practical. If we stuck them in there and left an air gap above them, then the periodic table would cover that whole wall. The other reason has to do with what we're going to discuss in a minute. Atomic orbitals, places where we put electrons. The electrons go into a certain orbitals here, and different orbitals here, different orbitals there, and different orbitals here. Okay, and I'll explain what that means in just a minute. So the structure of the table is set up so that we can determine where are the electrons going as we move from one element to the next. As we're building elements, we're adding protons, we have to add electrons. So where do the electrons go? The other important thing about this table is the division between metals and nonmetals. Metals are on the left of that black line. Nonmetals are on the right. And they have characteristics in common. Right. Let's see, do I have a slide on that? Yeah. Metals typically, if they are polished, they have a luster. Right? They reflect light. If they're precipitated out of solution and they're very thin layer, then they'll be black. But if you get enough of them together, then they start to reflect light and give you that luster. Or if you have a piece of metal and you polish it, it'll give you the luster. So that's not guaranteed. Thermal conductivity, very high for metals. They conduct heat very well. That's because the electrons are extremely mobile, and they can transfer that energy from one place to another. Same thing with electrical conductivity. Very high for metals. Malleability means you can mold them. You can bend, you can squeeze. If you have pure, let's see, let's take something that's not dangerous. How about iron? If you have absolutely pure iron, 99.999% iron, you can scratch it with your fingernail. It's soft, malleable. It only gets hard when we add things to it, like carbon, making steel. Okay, so those are metals. Oh, by the way, excuse me, I need to go back. When you look at the periodic table and you see all those metals on the left-hand side, on that periodic table the dividing line is red. On this one it's black. Well, the one that was up there is black. And I'll go back to it. Notice where that black line is located. Right? Horizontally it's between boron and aluminum. And then it stair steps. Aluminum, silicon, silicon, germanium, germanium, arsenic. If you start in the wrong place and you stair step, you're going to get that part of your extra credit wrong. Right? You got to start between boron and aluminum, horizontal, and then you can do stair step and you go all the way down and get it right. That divides metals on the left, non-metals on the right. Most of the periodic table is metals. and they're all solid at room temperature except for one. Any ideas? Which one's liquid at room temperature? They still use thermometers, or are they all that electronic stuff? They just stick a probe in your mouth? Yeah. Well, when I was growing up, they would stick a thermometer, well, either in your mouth or in the other end. And it had mercury in it. Mercury is a liquid at room temperature. So that's the one, see it's blue there, right? And that periodic table, when you fill it out, make reference to that one. Now, the nonmetals can be anything. They can be solid, liquid, or gas. And for instance, bromine is a liquid at room temperature. So mercury and bromine are the only two that are liquids at room temperature. There's some that are close, like gallium. If you take a chunk of gallium and put it in your hand, it'll melt. But at room temperature, mercury and bromine are the only two liquids. Gases, those are in red here. Nitrogen, oxygen, fluorine, chlorine, and then all the noble elements are gases at room temperature. And the rest are solids, like boron, carbon, aluminum, silicon, aluminum's a metal, excuse me, silicon, phosphorus, sulfur, arsenic, selenium, tellurium, iodine, those are all solids. Now, the solid metals are malleable. Right? You can squeeze them, you can bend them. They're also ductile. You can stretch them into a thin wire. But solid nonmetals are always brittle. Okay. And those are the characteristics in a single table. Now this is a previous edition, I think. Let's see. No, it's out of that edition. Right, that white version. These tables came out of that edition. And this just, puts it in a single table. There's the dividing line, right, just to make the point of how it goes down here. Most often when students make a mistake, they go out here under carbon and then they start stair-stepping between silicon and phosphorus and then arsenic and selenium, and then it just goes from bad to worse. Okay. Now we're going to talk about electronic structure. I need to get a new marker. The result of Schrodinger's work in producing those equations is that there are four variables, four numbers that are required to input into his equations to give you the outcome that would describe the most likely place of finding an electron around an atom and its energy. And those four numbers start with Bohr's number, the principal quantum number. Principal quantum number. And this is related to energy. Energy of the electron. And it can have, starting with 1, it can have 1, 2, 3, 4, on up. Whole numbers. Okay? I'm going to tell you what to do with them in a minute. Now, they say approximately the same energy. That's because once you get into the other quantum numbers, they modify the actual energy somewhat. and if you have multiple electrons and protons in the atom, they will also modify the energy. Because what happens if you have like 10 protons versus 2 protons in the nucleus? You have a stronger nuclear charge pulling those electrons. So N1 might be closer with 10 protons than it is with 2. Okay, so we need the other 3 numbers to actually tell us what the true values of what the other values are. We're not just talking about energy, but energy is very important. This is approximate energy level. Now this is called, your book is going to call this the shell. Anything described with that number is the shell. It also tells you, since we're talking about energy, it tells you the size of the shell. That is, if n is 1, the shell is going to be here, whatever its shape is. If it's 2, it's going to be out here. If it's 3, it's be here. So that's the size of the shell. Energy is also related to size. Okay? The subshell is quantum L is called the angular momentum, I think. Yeah, angular momentum. Quantum number. The angular momentum is also called the subshell. Now what it describes is the shape of the space where you're most likely to find the electron. Remember when I said Schrodinger's equations, the quantum mechanical theory is based upon probabilities. We don't know exactly where the electrons are located. Let's see. I want to introduce a concept that's not relevant. Well, I will say this, just to make the point. There was a chemist/physicist called Werner Heisenberg who mathematically proved that at these levels, well, actually at any level, but at these smaller levels, you cannot know exactly the energy of a particle and where it's located at the same time with any degree of accuracy. If you nail down the energy, then it could be anywhere. Or if you nail down its position, then you can't know what its energy is. So chemists have leaned toward energy. That's more useful information than knowing exactly where it is. So instead of saying exactly where it is, we say its energy is this amount, and it's probably in this space somewhere. That's more useful to do it that way. So this one, you'll see that in the literature as Heisenberg's uncertainty principle. Okay, so we've got, and these numbers, this is like a branching tree. So for each one of these numbers, this one is based on one of these numbers. Okay, and it starts off with 0 and goes up to n minus 1. So if we start at 1, there can only be one subshell, 0. Let me put the rest of them in here. Let me put these in here. Say 1, 2, say 3, and then on up to n minus 1. So if the principal quantum number is 2, then you could have 2 different subshells at that level. We can have one that's 0 and one that's 1, n minus 1. Okay. If we start off with n equals 3, then we could have a 0, a 1, and a 2. Because it's 0, 1, n minus 1 is 2. That's as high as you can go. Okay. So it's a branching tree, a root system. And To make things simpler, we leave these as numbers and we assign letters to these guys. Use S, P, D, and F for the subshells. And that'll become apparent to you when we actually write out the electronic structure for an element. Because if you put, say, 1, 2, I mean, how do I know it's 1 and 2 or 12? All right, so we use letters substituted for these, just to keep us from making mistakes. Okay, the next one is M sub L. And this is the angular, the magnetic quantum number. When I put hashtag, that's quantum number. Principal quantum number. Angular momentum quantum number. Magnetic quantum number. The magnetic quantum number is orientation. So this is the shape. So it could be, this S stands for spherical. So the shape of the orbit is spherical. Okay. Yeah. The p orbitals are dumbbell shaped. Right? They're like that, describing the most probable location for finding an electron in that region. And this center would be where the nucleus is located. Okay? You're not going to find any electrons at the nucleus. The d orbitals, it gets more complex, and the f is even ridiculous. So I stop here, especially for this class. The magnetic quantum number talks about orientation. So the orientation in three-dimensional space for the sphere, it can only be oriented one way, right? You can't change the orientation of a sphere. But if you have a dumbbell, you could set that dumbbell on 3 axes. You could have this y-axis, you could have the x-axis, or you could have the z-axis. Okay? Now here's how that works. This magnetic quantum number is based upon these guys. And it's minus L up to plus L, whole number movements through 0. Right? So if we're talking about what's the magnetic quantum number, what are the magnetic quantum numbers available for, say, a d orbital, which has 2, this would be minus 2, minus 1, 0, plus 1, plus 2. So you have 5 possibilities at this level for that subshell. And let's see, does this have a this is an orbital. Right. So shell, subshell, orbital. And the last one is the easiest one. Let's see. Oh, they didn't tell us. Okay, I'm going to tell you. The last one, M sub S, equals spin. And at any one of these levels, whichever one you decide, you can put 2 electrons in those, and that's it. In any one of these that we decide is, say, minus 1, it can only have 2 electrons with a plus 1/2 or minus 1/2 spin. So that's all you have available for M sub S. Now these numbers that we devise, that we extract from here, like we start here with that number, we only get one of these, then we could choose one of these, and then choose one of those. Those 4 numbers go into Schrodinger's equations, and they describe that particular electron in its environment. Okay. All right. Come on. There we go. So how many orbitals can you have with S as the principal quantum number? Well, 1, you can have that 0 there. That means you can only have one here, and that's it. You can only have one orbital with at principal quantum number 1. Or S, let's start at S. If it's S, you're going to have in one orbital. If it's P, you could have -1, 0, +1, or 3 orbitals. If it's D, we did that one before, you can have 5. And if it's F, you can have -3, -2, -1, 0, +1, +2, +3. 7. You can have 7 orbitals out of a subshell of F. Okay? Here's where that is applicable to our periodic table. Because for each one of those, you can have 2 electrons, which means you add 1 electron, which means 1 proton, add another proton, you get another electron. So you can have, for 7, for F, you can have 7 here, but you could actually have 14 elements as you increment up protons and electrons. Okay? Again, blank stares. Here's how it relates to the periodic table. Let's see, is that coming up? No, it's not. Okay, look at the periodic table. If we have F orbitals are being filled, so we got this F, and we're filling 7 orbitals, but we can get 14 elements out of it because 1 electron and then add another electron. So you get 14. Where do you get 14 in a group? Actinides, lanthanides. Count the numbers over there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Cerium to lutetium, 14 elements. Those are all being filled in the F orbitals. Okay? The alkali metals and the alkaline earths, you go from one to the other, you're going to got 2 electrons. Right? So where do you do that? You do that with this one, S orbitals. So those first 2 columns are S orbital fillings. You can only have 2 electrons, right? S is 0, you can only have 0, 2 electrons. That's it. Then if you move to the other side of the representative elements, boron, carbon, nitrogen, oxygen, fluorine, and neon, now you're filling sp orbitals. So p's would be here. 1, you could have -1, 0, +1. That's 3 orbitals or 6 elements because 2 electrons for each orbital. If you look at that, boron, carbon, nitrogen, oxygen, fluorine, neon, 6 elements. So the first 2 columns you're filling s orbitals, the last 6 you're filling p orbitals, and look at the transition metals. Scandium to zinc, there are 10 of them. So that means 5 orbitals. Where do you have 5 orbitals? D's. -2, -1, 0, +1, +2. 10 elements, 5 orbitals. So you go across there, you're filling d orbitals in the transition elements. That's the way the periodic table is arranged. And if you know that, you can use that to actually write the electronic configuration of any element. I'm going to give you some examples in a minute. If I don't waste all our time. These are examples of the shapes, right? Subshell shapes. Like I said, f orbitals can get really wonky. These are p orbitals, right? They're the easiest ones for me to grasp intuitively because they're on each of the 3 axes, x, y, and z. Oh, there's the spin. Okay. Spin is kind of a, I don't know that the electrons are actually spinning, but it fits into the equations. Spinning clockwise or counterclockwise, positive or negative. And you can't put 2 together that are spinning the same direction. They have to be spinning opposite directions in that orbital. All right. Now, when we're doing this, there are certain principles that have to be observed. One is the Aufbau principle. which is German. I think it just means do it this way. Actually, what the Aufbau principle means is as you build atoms, one proton and one electron at a time, go from left to right and top to bottom, you put the electrons in the lowest next available energy level. You can't skip an energy level for a basic atom. The other is Hund's rule. Electrons occupy the orbitals of a subshell such that each orbital acquires one electron before any orbital acquires a second electron. Okay, here's what we mean by that. If we have a subshell of, say, P, so we have a P subshell, how many orbitals can you have? 1, 2, 3, correct? -1, 0, +1. Okay? If you're putting electrons in there, say you go one element, and this element needs an electron, right? +1/2, spin up. If you got another electron, you go into the next element, you're going to put another electron in there. You can't put it next to that one yet. Hund says you have to put it over here. And then if you put another electron in, along with its proton, you put it over here. Then if you go to one that has the next proton and electron, now you can go back and pair them up. That's Hund's rule. It's simply based upon the fact that these guys have the same charge, so they need to be as far away from each other as possible. So you put them in separate orbitals until you can't, until you have to go pair them up. And there's going to be some repulsion in here too, but they do have to be opposite spins. That's Hund's rule. Now these are called, these are at essentially the same energy level, and these are called degenerates. Degenerate orbitals. And in chemical terms, degenerate means same energy. It doesn't mean, perverted. Okay, and the last principle we have to observe is Pauli exclusion principle. Pauli was a brilliant scientist, and he proposed this idea that in Schrodinger's equations, if you're comparing that's one way to put it. Here's the way I would put it. No two elements, no atoms of two different elements can have the same set of 4 quantum numbers. They have to be unique quantum numbers. Actually, that's true, but within the atom, you can't have any 2 electrons with the same set of quantum numbers. So that would be a better way to put it. Let's see. Let's see. No 2 electrons can have the same set of 4 quantum numbers. Right? The quantum numbers that are assigned to any one electron in an atom are unique to that electron. Okay? That's the Pauli exclusion principle. So if they have the same numbers here, here, and here, they have to have opposite spins. Okay. Now here's the problem. As we start to fill, if we follow the Aufbau principle and start to fill electronic orbitals, next highest energy, as you get more and more protons and more electrons in that mix, the order changes. So shorthand. This is the shorthand way of writing an electronic configuration for an element. Principal quantum number, and then So principal quantum number 1 and then S would be the lowest energy possible for any atom. And we could have 2 electrons in it maximum. Hydrogen would only have 1. So this would be hydrogen. If we had helium, then we would have 1s2. Because you can only have an S in a 1. So we're going in order. As we add protons, we add electrons. And then we go to the next level, right, which is 2s. So this would be, let's see, lithium has 3 electrons. 3 protons, 3 electrons. That one's filled. This one can only have 1. Now, for a while, they're in reasonable order, right? 1, 2, 3, 4, and then these guys on top. But after you get so many in there, they start to switch. So you notice there at the bottom is the 1s. And then you get the 2s and the 2p. Then you get the 3s, 3p, and when you get to 3d, actually 4s is lower energy than 3d. So you have to go 4s next. All right. There's a practical way to approach that, and it's called the diagonals. Actually, there's a simpler way, but I'm going to show you this way first. So if we set up the orbitals, so we have 1s here, 2s, we have all the s's here. See, how far down did I go? I did down to 6, 7. 6s, 7s. And then we put the p's. 1 can't have a p, right? Because 1 can only have s. Can't have that. But once we get to 2, now we can have a 2p. But we can't have anything more than that. 3s, we can have a 3p, and we can also have a 3d. Why? Because 3 has 0, 1, and 2, SPD. Okay. 4, we can have 4p, 4d, and 4f. 5, we can have 5p, 5d, 5f. Actually, there's a g, but we don't have enough elements to use G, so I stop at F anyway. And this is 6P and 6D, and then 7S and 7P. I think that's probably all we're going to need. So, filling them in order of energy. You go like this, fill that one first, and then you circle back, take that one, then you take this one and that one, then you take this one and that one, this one, that one, and that one, that one, and that one. So this says you fill the 1s first, and then you go to the 2s, 2p, 3s, 3p, 3p, and then 4s, and then you go back up to the 3d, 4p, 5s, and back up to the 4d, 5p, 6s. That keeps them in order of energy. Now that's one way to do it. The easier way to do it is to know how the periodic table is arranged. Okay, so notice the way we've got it arranged, the period 1 is principal quantum number 1. So hydrogen is 1s1. Then you move across to helium, 1s2. Then you go back down to lithium is 2s1. Beryllium is 2s2. It's got the 1s's in there already. Right? We're just adding orbitals to them. Then you go over to boron. Now we're into p's. We're at 2p1. Yes, p. That's right. Carbon is 2p2. Nitrogen is 2p3. 2p4, 2p5, 2p6 is neon. Okay? Then you circle back. You've got the 1s and the 2s and 2p's filled, so you got to go to the next level is 3s. Sodium is 3s1, magnesium is 3s2. Aluminum is 3p1. Silicon, phosphorus, sulfur, chlorine would be 3p5, and argon would be 3p6. Then you go back to potassium, and you got 4s1, calcium is 4s2. Now you got to go to the 3Ds. Right? So you're in the fourth period, but you haven't got the 3Ds done yet, and they're next. The 3Ds are next. They start with scandium. So you got 4s2 for calcium, and scandium is 3d1. Then titanium is 3d2, vanadium is 3d3. Chromium is squirrely. I'll tell you about that one in a minute. But you're filling the d orbitals across there. Then when you get to gallium, you go back to 4p. Just like we did in that diagonal. Go back to 4p. And you get across to 4p6 is krypton. Then you go down to the fifth group, and that's 5s1 is rubidium, 5s2 is strontium. Then you go to 4p1 is yttrium. Okay, so when you get to the Ds, when you get to the transition metals, you have to come back one principal quantum number. All right? Let's see. How about nitrogen? Let's do nitrogen. So first you have nitrogen. How many protons, how many electrons? 7. Right. 7 protons, 7 electrons. So our first energy level is 1s with 2 in it. All right, we've used up 2, we've got 5 more to go. So we go back to 2s2, fill that one up. That's 4. We got 3 more to go. So now we go to 2p. 2p3. That's nitrogen. Okay. Now why does that matter? Well, it matters because of that concept we looked at earlier called valency. The electrons that are available for reaction are the highest energy level electrons. The highest principal quantum number. So these are the ones that are available for reaction. These are core. These are valence. They're the ones that can react for nitrogen. Now, look what we got here. We got 2, 3. How many more P's would it take to fill this up? 3 electrons, right? If we had 3 more electrons, we could fill that up. So if nitrogen reacts with something and it gets 3 electrons from some other element, it can fill those up, and it's really happy because it looks like argon. Right? Argon would be full across here. That's the nature of the noble gases. They have full orbitals. That's why they don't react with anybody. But if you're missing electrons and you can arrive at full orbitals at highest energy level by either accepting electrons or getting rid of them to leave behind whatever, then a tendency toward noble gas configuration is what drives the reaction. In any of the other courses, have you heard of the octet rule? No? Okay. Sometimes you get it in biology class, sometimes in anatomy and physiology. The octet rule just simply says that a full set of electrons for period 2 and period 3 is 8 electrons. So you count them. Look, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. That's 8. That's the octet. If you can complete the octet for periods 2 or 3, you've got a happy element in a reaction. So, nonmetals like to accept electrons, like nitrogen, because accepting electrons, 3 electrons, will get it to neon. Metals like to give up electrons, like sodium. If sodium reacts and gives up 1 electron, now what does its configuration look like? Just back up 1, right? Sodium's 11, back up to 10. Now sodium's electronic configuration looks like neon, and it's perfectly happy. Should I illustrate? Or should I leave well enough alone? Let's see. Right. This is what's known as the condensed notation. For elements high in the table, this is perfectly fine. When you get to bigger elements, we need to abbreviate the notation even further. Now, the authors use up and down arrows like this, double barbed arrows. That's too much work. With boxes, I just put a line like one orbital there, 2 electrons. One orbital there, 2 electrons, right? 1, 2, 1, 2, 1, 2, 1, 2. Here, right, this is a p orbital, so it has 3. 1, 2, 3. So that shows you where the electrons are in the orbitals, right? This is a shell, subshell, these are orbitals. So that's what a neutral nitrogen atom would look like, electronically speaking. How about sulfur? Okay, sulfur, let's see. So you look, 14 protons, 14 electrons. So we've got 1s, 2s, 2p. This has 2, 2, and 6. What is that, 10? So I got 4 more to go. So I'll circle back to the 3 s's, use up 2 of those, then I'll go to the 3 p's, use up 2 of those. That's 2, 4, 6, 8, 14. So that's what sulfur would look like. And if you look at the periodic table, you notice that sulfur is 6 steps over from sodium. Sodium would be, let's see, sodium would be down here with 1s. And then magnesium would be 2. Oh, I didn't go far enough. Oh, I put the wrong number. And you didn't catch me. I was looking at the wrong. 16. There we go. So if we count from left to right, in the P group, right, we have aluminum, silicon, phosphorus, sodium. Aluminum, silicon, phosphorus, sodium is 4 electrons. Okay. Now barium is another animal. We could do barium right all the way out, but barium has 56 protons, 56 electrons. We're going to abbreviate it even further. We're going to say backup barium, cesium, xenon. Xenon has 54. It's complete. That's a core. Xenon, 54, leaves us with what? Only 2 electrons. Where do they go? Well, we're in the 6th period, so it's 6s. That's barium in abbreviated form. Right, there it is, long and drawn out. Right? And shorthand notation does that. Okay? I'm not going to give you any that you have to write out like barium, unless I say you can use shorthand notation. And then you just back up to the nearest noble gas, use that as your core, and then say what's beyond that. That's what we should have, yeah. Yeah. Uh-huh. Yeah. And of course you'll have this one, but it's kind of hard to see that one, so there should be one with the test. Yep. All right, the electronic configuration of sodium is, I'm not going to waste any time, except to say that, look, 3s1, that Does that look reasonable? 3s1. Sodium, well, yeah, it's in the third period, and it's the first one in the period, so it's a 3s with 1 electron. Now there are 2 others in there like that, but they have other flaws. Okay, what you'll notice is the electronic configuration in the valence shell, the outermost shell, is similar for all the elements in a group. That's why they have similar chemical behaviors. Mendeleev didn't know that at the time. He was just observing their characteristics. But this is why he observed that. All the elements in that group have similar outer shells. Okay, to illustrate, lithium, sodium, potassium, they're all alkali metals. Their highest energy level is s orbitals with 1 electron. So since they're metals, they want to lose an electron. Say potassium. What would potassium look like if it lost 1 electron from that 4s orbital? Back up 1. It looks like argon. Right? It only has 18 electrons now. It has 19 protons, 18 electrons, so it looks like argon, electronically speaking, and that makes it happy. But in order to do that, it has to gain a charge. Right? You've lost a negative, so what does that mean? You've got an excess of 1 positive. Right? So that makes potassium like that, electronically equal to, what did I say? Argon. All right. Okay, so there's your arrangement. There are some anomalies in the electronic configurations, especially in the d orbital fillings, but I don't think we've got the mandate in this course to go into those. This just gives you a general appreciation for how the periodic table is built and why it's set up that way. I'm not sure what they're getting at here. Distinguishing electron. The last electron added to the configuration of an element when the subshells are filled in order of increasing energy. It just means that when you add that next electron, it's different than the one before it. Right? Okay. Let's make a big point out of it. All right. I think this is just reiterating. Elements are divided into metals and nonmetals. They're described, they have different names. Right? The inner transition elements, the lanthanides and the actinides are inner transitions. The transition metals in elements in general are the ones who are filling d orbitals. The inner transitions were filling f orbitals. There we go. There, representative elements. Okay, it did make a point. So the s orbitals and p orbitals, all those groups together are called representative elements. Okay, elements in group 1 and 2, they fill the s orbitals. All right. Okay, 9 minutes before you get a break, right? 11:30? Yeah. So let's see if we can make sense of this one. Consider 2 elements. One is a gas and the other is a solid. So we got an element here that's a gas, and we got an element here that's a solid. Call it, we can't call it Y because that's yttrium. Let's see. What can we use? A. We can use A. There's nothing up there with an A. Oh, there's nothing up there with a Z either. Let's use Z. There we go. Two different elements. Each contain identical number of electrons in their outer shells. Okay, so they have the same valence structure. These elements are, and out of the selections that we're given, let's go in there and decide how to analyze these. If the first one is a gas and the second one is a solid, how about A? Is that one a candidate? Yeah, fluorine's a gas, iodine's a solid. So A's okay. At this point. We'll go back and look at the numbers in a minute. Gas and solid for B? Yeah, B, that's right. Nitrogen. This is fluorine, iodine. The second one is nitrogen and sulfur. Okay, that still works. Oxygen and sulfur, that still works. And the last one, fluorine and iodine again. Okay, so they met the first conditions of state, gas and sulfur, all of them. So now, each contains identical number of electrons in their outer shell. These elements are blank and blank, and they contain blank electrons and blank neutrons, respectively. Blank electrons. Oh, they contain, the first one contains so many neutrons, the second one contains so many neutrons. Okay, so we want to say how many neutrons they are. All right, let's look at it this way. Fluorine is 9 protons. Iodine is 53 protons. We'll come back in a minute. Nitrogen is 7, and sulfur is 16, and this is 8. Okay? Now, what's the most common isotope? That's what we have to decide. The most common isotope for each one. We look at the values for fluorine. It's 18.999. The most common isotope is probably 19. Excuse me. 19. Okay? Iodine. Its number is 126.9. Yeah, so its most common isotope is 127. I just rounded off to the nearest one. How about sulfur? No, I didn't do nitrogen yet. Nitrogen is probably 14. Yeah. Oxygen is 16. Sulfur. Most common for sulfur would be 3206, be 32 would be its most common isotope. And iodine is 127. Okay, so how many neutrons do you have here? 10, right? 53 from 127. 74. Is that right? So 10 and 74, we found our answer. It's A. Okay? So probably the trick to answering that question is knowing how to decide which isotope to use. And if you look at the atomic mass, then you're going to get a number that's closest to the most abundant isotope, just simply by rounding it. All right, how about this one? What time? Have 4 minutes. Okay, you're asked to determine the composition of a gas. There are 3 components with 3 different applications. Composition of gas. They all have the same atomic number, but the number of neutrons is 0, 1, and 2 respectively. 3 components, 3 isotopes, with 3 different applications. That's true. Generally, different isotopes serve a different purpose. The number of neutrons is 0, 1, and 2 respectively. One of the components is used as a radioactive tracer, biological experimentation. Identify the gas you were given. And how are the 3 components referred? In other words, do the isotopes have names? So if we look at the first one and say carbon, at isotopes 12, 13, and 14, is carbon a gas? No. None of those are gases. How about hydrogen? Yeah. So B or C could be, right? Those are gases, right? I'm logically eliminating the ones that don't work. And oxygen, well, oxygen's a gas also, right? So we look at B, C, and D. The next thing is they have the same atomic number, which is true for all of them. But the number of neutrons is 0, 1, and 2. Would oxygen fit that? No. Oxygen's got a lot more neutrons than that, right? The oxygen 16 would have 8 neutrons. Oxygen 15 would have 7 neutrons. All right? So oxygen can't work. It's got to be B or C. It's got to be hydrogen or, oh well, now we're looking at the special names. How are the 3 components referred? Are they referred to as elements or as isotopes? Isotopes. So we found B is our best answer, and see if the rest of it works. No neutrons, protium, right? This is like that and like that. No neutrons. Deuterium is like that and like that. Tritium is like this and like that. So that's your answer, B.